got a couple people in second period that are not with us right now. They're live. They're just not in class. Let's see. So homeworks are open till end of the day tomorrow. For anybody that hasn't finished the homework yet, there's a little extension. I'll send out an email to everybody, just reminding y'all. The test is open. Hey, you need to do the test. You can do it this class period or sometime today, but make sure you get it done. So the test is open for the people that haven't taken it. I've got a couple in the next class period too. And let's see. This is really the last week of class. We're gonna blow through a couple chapters today because I just want to get through them and talk about some important things that I might see. But it's going to go really quickly. I'm going to skip a lot of slides. I'm going to try to get through maybe a chapter and a half today, maybe 2 full chapters. Tomorrow we'll finish up the chapters, I think, and then maybe Thursday I'll start on the what's it called? The signature assignment. I'll give you all the signature assignment papers. And we'll talk about those questions and how to answer them. I misremembered what the signature assignment was. I thought it was more of like a weather mapping thing. And I guess my weather map thing was like a separate lab. And so maybe we'll squeeze that in next semester. It does look like I'm going to get set up for next semester with the new different book. And so I will give you all information about that coming up. I still have to get everything squared away with the book publisher, but expect that. And let's see, early next week, we'll start off with the SLO, which is like basically a practice test review. It's not a practice test; it's part of your grade, but like a review for the final in a way. And then we'll, I guess, review a little bit. I guess we can go over a couple things, hit some big issue topics, and review for the final. We'll discuss the final and take it next week, and then we'll be donezo. So I'm thinking the final either on Wednesday or Thursday, because I want to do it early because everybody needs to take it by Friday. So if anybody's absent, I want to give them plenty of time to get it done. If you know you're going to be absent later in the week next week, you need to let me know early, because an incomplete here is pretty easy. If I got to put an incomplete in with you for you at Navarro, they're going to ask a lot of questions, and it's going to be an issue. So do try to make sure you're here for the final exams. I know y'all have other dual credit classes, so you'll be here for those exams. So yeah. So we've already talked about the atmosphere. I think chapter 11 was what? The atmosphere and energy. This is not the chapter 11. Here we go. Yeah, it's our atmosphere, and they basically talked about energy input into the atmosphere, how we get our energy from the sun, how things reflect. We talked about albedo. And now we're going to move into moisture in the atmosphere. Moisture, clouds, and precipitation. We did not start on this last week, did we? I don't think we did. Did we? Yes, because it talked about latent heat and calories, didn't I? All right. So we did go through at least some of this. Heat energy, solid, liquid, gas. Yeah. We talked about latent heat and these different temperatures. We talked about hygrometers and how we measure humidity in the air. Adiabatic temperature changes. So this is changing temperature without actually changing how much heat you're putting in. So you're changing the pressure or you're changing the elevation, and it's changing the temperature. So yeah. So like this air, as it rises, isn't actually losing any heat. It's just getting higher and higher and higher with less pressure, and so the temperature is dropping. Even though technically the air has the same amount of energy in it, that energy is not working the same because the pressure has changed. We talked about orographic lifting with wind being lifted up, so it drops all the rain on the windward side and is dry as a bone on the leeward side, which gets you these rain shadow effects like we see in the Pacific Northwest. I think I pulled up Google Maps and kind of showed that to y'all. Frontal wedging, which I kind of mentioned that we would do in the signature assignment, but I guess we're not. We saw this neat picture of all the clouds over Florida, kind of outlining the shape of the state. Wonderful. Localized convective lifting, I think that's about where we left off. Let's see. So they're talking about stability of air. Stable air is basically going to want to stay exactly where it's at. It's not going to have adiabatic cooling. It's not going to want to rise or sink. Well, I guess it says it wants to sink, but it doesn't want to rise. It wants to be the same kind of air package as it is. And so it's not really going to change a whole lot. Unstable air is going to rise like a balloon. And so they talk about absolute instability. It's adiabatic cooling, which is going to allow it to drop moisture out and produce some precipitation. And it really depends on what's going on, but there are air packages that don't want to change and air packages that are easily changeable. And so this is illustrating absolute instability as it rises up. It passes that adiabatic line and starts to produce precipitation out of its moisture. So conditional instability, this depends on what's kind of pushing it up, but it allows itself to rise as this little cold air wedge comes in and pushes it up. Condensation, we all know what condensation is. If your temperature drops, the air in that now colder temperature cannot hold as much moisture. And so the moisture that was in there before was perfectly fine, but now that it's colder, that moisture has to go somewhere because the air can't hold it. And so it condenses on your car window, on the grass, and then if it gets cold enough, like this morning, drops down below the freezing point, all that condensation ends up freezing, and you have to like scrape your windshield off or run your car for a little while before you leave. Did anybody have to do that today? Scrape their windshield? Yeah. I started my truck early enough where I didn't have to do it, but I did drive like this for the first part, looking underneath the top icy part. Then they get into the different types of clouds, which are actually cool, but I can never seem to remember the names for them. We've all heard the names: cirrus clouds, cumulus clouds, stratus clouds. You also have cumulonimbus clouds. And this is a nice little image to kind of go over any of them. So if you see any cloud questions on the final exam or on the SLO, know that you have an image in the book that kind of has them all laid out for you and shows what they look like. So your cumulonimbus ones are going to be the big storm clouds that we get here in Texas. So if we've got thunder, tornado possibilities, and heavy rain, that's going to be cumulonimbus. The rest of them are just kind of regular clouds that go around. Cumulus are your regular puffy clouds. If they're small and puffy, like little cotton balls, that's stratocumulus. Stratus are the low, flat ones. Nimbostratus, we don't get a lot of those here. Little rain clouds that are kind of isolated. And then you have your upper wispy clouds that kind of get stretched across the sky. Some more cotton ball clouds, depending on the level that they have. So yeah, lots of different names for lots of different clouds. Here's some more pictures. You got cirrus clouds. You got cirrocumulus clouds, altocumulus clouds. And what is this? Cirrostratus. I don't see any clouds in this picture. Maybe a couple like right up here. Very wispy clouds. Mostly just a picture of the sun. Okay, so high clouds, middle clouds, and low clouds, these are all about altitude. So if it's above 6,000 meters, it's a high cloud. If it's 2,000 to 6,000 meters, it's middle. And low clouds are below 2,000. So whenever they talk about low clouds and fog and anything like that, it's below 2,000 meters. More pictures of clouds. Wonderful. Clouds of vertical development. So now they're talking about the cumulonimbus, the big storm clouds. Okay, this is actually kind of important. You might see a question or two about this. What is the function of condensation nuclei in cloud formation? Basically, when you have moisture in the air and something changes in your air package to make that moisture have to come out, it can't just like pop out of nothing. It needs something, like those water molecules need something to form around, and that's what condensation nuclei is. It's either other particles of, for lack of a better term, pollution or smoke or dust or sand, anything very light and very, very small that might happen to be floating around in the air. If those things are there, which they pretty much are always there, there's different levels of them, and it depends on what part of the world you're in. But for the most part, they're always there. That is what the water droplet is actually going to form around, which is one of the reasons why when you go outside in the morning, there's water on your windshield and water on the grass, but it's not raining. Like, it doesn't feel wet outside. You just see the moisture on the grass because the grass and your windshield acts as that condensation nuclei. It's a surface for the water to actually come out of gaseous, come out of like the gas format into the liquid format. So it has to have something to kind of form around, and that's what the condensation nuclei is. And it kind of says it right in the name. Condensation, going from a gas to a liquid. Nuclei, it's the center of that process. It has to have something to form around. So they talk about fog. Most fog forms because of radiation cooling or movement of air over a cold surface. And so normally we don't get a lot of fog here. But if you ever live near a large lake, you might get a lot of fog. What's the probably the fog capital of the United States?
Seattle?
Yeah, San Francisco. Seattle probably has quite a bit too, yeah. And those are because those are near bodies of water where warm air is allowed to blow over cold water. And that kind of cools it down and creates this fog effect. If you ever go to San Francisco and you want to get a picture of the Golden Gate Bridge, know that you're probably out of luck. It's going to be covered up in fog, and you're just going to get the part of the bridge that you're closest to, not the whole thing. So as a person that lives in a place that doesn't have a lot of fog, I wouldn't know that they have all sorts of different names of fogs. So they have advection fog, radiation fog, upslope fog, and they're all just kind of formed in slightly different ways depending on how the air is moving. I don't think you're going to see a lot of fog questions. But yeah, this is what normally is going on in the Golden Gate Bridge. This is probably a good day. Most of the time, you do not get to see the majority of the bridge. Same thing goes with, why can't I think of things in the morning? The prison island out there, Alcatraz. Everybody's like, oh, where's Alcatraz? And they point, and it's there. You just can't see it because it's surrounded in fog most of the day. Also, yeah, that's what made it kind of difficult to escape. I mean, obviously, it's an island and you have to swim to shore. Swimming to shore is not impossible. But when you get outside, you can't even see which direction shore is because you're surrounded by fog for a good portion of the year. So here's some more fog. This is fog they actually saw on radar. That's actually a pretty big piece of fog. Probably coming off the Pacific Ocean here. The air is affected and creates fog. Here's a warning about fog. Evaporation fog. So they got some more different types of fogs. You have steam fogs, frontal fogs, precipitation fogs, precipitation fogs. I almost said frogs. And you can see it kind of coming off the lake here. And so this is normally the kind of fog that gets produced. When we have fog in Texas, it's usually just really low clouds. And so we call it foggy, but it's not necessarily the same type of fog that they're looking at. So here we go. Days with heavy fog, we are literally in between like the two lowest things. We get almost no fog here in Texas. Areas around bodies of water on the West Coast, around the Great Lakes here, and the Great Lakes get a lot of fog. That moisture, depending on the temperature, can also turn into snow. They call it lake effect snow. So everything along the Gulf, everything along the West Coast, Central part of the country, not so much. Cloud droplets and the Bergeron process. So the temperature in the cloud is super cooled. Ice crystals collect water vapor. Large snowflakes form and fall to the ground and or melt and turn to rain. So they're just kind of showing how water droplets and snowflakes build up in the atmosphere before they fall down to earth. So you have something kind of start the process, and then you have all these moisture H2O particles in gas form that are hitting that, and they're going to add to it and kind of collect up, and it's going to build up and get bigger and bigger and bigger. They do have actual sizes for precipitation. So cloud droplets are usually less than 20 micrometers, so less than 0.02 millimeters in diameter. They fall incredibly slow because the wind is very easily pushing them back up. And they're like the beginnings of precipitation. And the idea is, as one of these water droplets falls, the further it falls and the closer it gets to the ground, it's just hitting more and more smaller water droplets, which are all collecting into the larger droplet that happens. And so it just builds up and gets bigger and bigger and bigger. At a certain point, it's too big to fall in one piece. And so the wind will kind of tear it apart into smaller droplets, which will then get bigger and bigger. And so, we see that with rain. Sometimes it's little tiny droplets that just kind of sprinkle down. Sometimes it's big old fat drops that smack on your windshield. And so it depends on how much water you have and how far the droplets have fallen. So when they talk about rain and drizzle, those are technically specific sizes of droplets. So for regular rain, droplets have at least a 0.5 millimeter diameter or bigger. For drizzle, droplets have less than 0.5 millimeter diameter. So it's not just the amount of rain that's falling, it's the size of the droplets. They also mentioned snow. Obviously, snow is frozen rain, aggregates of ice crystals. Sleet is going to be frozen, larger pieces of rain, where snow has your nice snowflakes. Sleet is going to be, sleet, little pieces of frozen water droplets in a way. Small particles of ice in winter occurs when warmer air overlies colder air and rain freezes as it falls. And then you get a glaze or freezing rain. Impact with a solid causes freezing. We get this in Texas more than we get sleet or snow. It rains and the ground is cold. When the water rains down, it's still liquid. But when it hits the ground, it's going to freeze and form nice ice sheets on our roadways, which makes all of us bad drivers. And then hail, we also do get hail. I don't know if we get hail more than other parts of the country, but it feels like it's always threatening with our big clouds. So hail is going to be larger pieces. Most diameters range from 1 to 5 centimeters. Obviously, here in Texas, we can get them big, like softball. Softball sometimes. Softball is very, very rare. But golf ball size hail causing pretty large dents. I guess the truck I bought a while back has a bunch of hail dents on it, like pretty much everywhere. It's a lost cause. It's also nice because somebody dings my door in the grocery store parking lot. I don't really care. There's dents all over it. So, this is a large piece of hail right here. And it looks like they've had it cut open so you can see all the concentric rings of how the hail just built up over time in the clouds. And basically what happens is as things are coming down, you have updrafts happening in the cloud as well. And so if the hail is small enough or if the updrafts are large enough, they just keep pushing the hail back up into the cloud where it falls back down and gets bigger, collects more rain around the outside, then gets pushed back up. So the more it gets pushed up and falls down, the bigger it's allowed to kind of build up into. So strong updrafts are going to produce very large hail, which obviously can smash your windshield and dent your car. Rime is where you have frost forming on cold surfaces. This is basically, the sublimation, where it goes straight from a gas to a solid. So it's the freezing of cloud droplets, very, very small particles of water in the air, and it's going to freeze directly onto surfaces. In this case, this poor plant here. So, explain why snow can sometimes reach the ground as rain, but the reverse does not occur. What? Explain why snow can sometimes reach the ground as rain, but the reverse does not occur. Because if rain were to freeze, it wouldn't turn into a snowflake. It would turn into sleet or hail. Snow has to form in a very particular way, where if you just freeze rain, it's going to be, like they say, sleet or glaze, not snow. So, measuring precipitation rain, we're almost to the end. Rain is the easiest form to measure. You just get a rain gauge. Who's a rain gauge at their house? Telling you, you hit like 30, 35, someone gives you a rain gauge, all of a sudden it's super important to you. Yeah, every time it rains, you're going to go outside and be like, how much did it rain? Did I get an inch? Did I get 2 inches? What happened? I don't know why. It's just a weird thing that happens. My rain gauge got like bleached by the sun and is now unusable, so I need to get a new one. So just a weird thing that happens in life. We also use radar to measure the amount of rainfall. So that's actually something that is, within my lifetime, I guess, a relatively new development. What do they call it? They have a particular name for the weather radar. But anyways, I think if you drive south on 35 or 45, I don't remember, there's at some point down there, like maybe down towards the Slovachecs and West Texas, west of the town, not the location. There's like this big tower with a white ball on top. That is the weather radar. And so if you ever look at a weather map and you see like the arm that sweeps out and kind of changes all the weather every minute, the center of where that arm is sweeping out on the map is the weather radar. And so you can kind of see those sometimes as you drive around. But yeah, this is what happens when you have a rain gauge. It just collects a certain area of rainfall and it comes down and tells you how much rain you got. This is just a weather map showing how much rain these people are getting. So is it heavy precipitation or light precipitation? And snow has 2 measurements, depth and water equivalent. This is actually pretty important for snow. Like I said, we don't get snow here, so it's not a big deal for us. But the depth of the snow is important for us because, like, how deep is it? Do I have to wear boots? Is the snow going to be up over my ankles? Am I going to be able to drive in it? Do I have to shovel my my sidewalk in my driveway? But the real important thing for meteorologists is how much water is it worth? Because you can have dense snow or you can have really light, fluffy snow. And eventually all of it's going to melt and it's going to have to go somewhere. So knowing how much water is actually there is important. So in general, the ratio is 10 snow units to 1 water unit. So if I have 10 inches of snow, that's basically the same as 1 inch of rain. And so it does vary widely depending on how much snow you have, what kind of ice, how packed it is. There's all sorts of different things that can change that, but that is kind of like an average. And huzzah, we're through chapter 12. Let's begin on chapter 13, which I already have pulled up. PowerPoints. Atmospheric motion, what is this? 34? That's pretty good. I can probably get through this quickly. So the atmosphere in motion, how does the atmosphere move? We start with air pressure. Air pressure is the force exerted by the weight of the air above. We have 1 atmosphere above us. There's lots of different ways to measure this. We have pounds per square inch, which is how we measure pressure in our tires. We have kilograms per centimeter squared. So instead of pounds, we use kilograms. Instead of square inches, we use square centimeters. So kind of the same measurement, just different numbers used. We also have millibars, which is another way to measure pressure. We have inches of mercury, which is another way to measure pressure. This was probably the first way that we measured pressure. They would literally have mercury. Well, they'll probably have a picture of it. They literally have mercury in a tube. Here's the tube. You have a pool of mercury down at the bottom. The more the air is pushing on the mercury, the more the mercury pushes up into the tube. And so literally millimeters mercury is measuring how many millimeters of mercury you have pushed up into your tube. So yeah, that's pressure. As you go up in the atmosphere, so like if I'm up here, I have way less air pushing down on me than if I were down here at the bottom, which is why when you go up to higher elevations, there's less air pressure. It's harder to breathe for people that are used to lower elevations because we're literally not getting as much air forced into our lungs for every single breath that we take. So you gotta adjust your breathing, and your body's got to compensate for that lack of oxygen. They have mercury barometers, which I talked about. That's your millimeters mercury. It's just a glass tube filled with mercury. An aneroid barometer without liquid aneroid uses an expanding chamber. And then you have a barograph, which continuously records the air pressure, and it's probably a little bit more modern. So here's your barograph, more almost like a seismometer. It's got the rolling piece of paper, and it just constantly records the pressure. Here's your millimeter mercury bath. You can see the mercury. The more air pressure there is, it pushes down, which pushes more mercury up into your tube. And then this is like a spring barometer. If you have like a outdoor thermometer, a fancy outdoor thermometer, it might have one of these. The more pressure there is, the more it kind of pushes on the spring and changes your little pointer here. So nice. Describe the operating principles of the mercury barometer and the aneroid barometer. I just did. Horizontal movement of air. So basically, all the air that's moving is because of pressure. Some of this pressure changes because of temperature, but all the air moving is moving because of pressure. That is wrong. Sometimes when it's wrong, you just see the second hand like ticking in the same spot over and over again. I'll have to change it. But it's almost time. Oh, we got a little bit. We got like 10 minutes still, right? Yeah. Okay. So all the air that's moving, basically all wind is going to be because of pressure. Wind is going to blow from a high pressure to a low pressure. Know that on the Earth's surface, most of that pressure difference is because of heat and the sun's energy, but still, just from one hot area to a cold area, the wind is not going to blow unless there's a pressure difference. And so there's always got to be some sort of pressure difference for wind to blow. When we look at that on the map, we look at isobars, which have lines of equal air pressure, and it kind of shows you where the pressure is high and where the pressure is low. So you're looking for that pressure gradient, and they're not really going to show you a map just yet. But you can see here, you have a steep pressure gradient. So I go a large pressure change over a shorter area. This is going to give me stronger winds. Over here, I can go over that same area and not have very much of a pressure change at all. So there's still going to be wind. As long as there's a pressure difference, there's going to be wind. But the winds are going to be much weaker because I'm just not changing that much pressure over that same distance. So here's an example. This is going to be pressure over the United States. You can see these numbers here are not temperatures, they're pressures. And this is an indicator of the wind. So it shows you which direction the wind is going and how fast it is. And you can see here, this is low pressure and this is high pressure. So in areas where you have several of these lines all spaced close together, you have a pretty high wind going from high to low, high pressure to low pressure. The wind's actually moving pretty fast. It's that one looks like it's maybe this symbol. So 61 to 66 miles per hour. That's a pretty good wind. That's a very windy day. Now, obviously, this is probably upper atmosphere. As far as like ground level wind, that would be pretty fast. That'd be like an extremely windy day. But that's a lot of wind blowing right there. Where over here, you have a large distance that has no pressure change or no real like stacking up of lines. You have very, very low winds. You're talking 1 to 2 miles per hour, very, very calm over here. Because you're just not changing pressure across most of, what is this, Colorado here? So there you go. No wind in Colorado. Very strong winds in Wisconsin. It's funny, after the presidential elections, I know all my states a lot better. And then like 3 years from now, I'll be like, I don't know where Wisconsin is. What do you want from me? Coriolis effect. We all know about the Coriolis effect. We've learned about it in school. It's the deflection of wind based on the rotation of Earth. So it's the apparent deflection of wind in the direction due to the Earth's rotation, deflection to the right in the northern hemisphere and to the left in the southern hemisphere. Another thing that affects wind is friction. Friction is always going to slow down your wind, which is why on that previous page, I was like, well, 60-something miles an hour wind, that's probably in the upper atmosphere, because it's actually very difficult to get winds that fast at the surface. Usually to get 60-mile-an-hour winds, you have to have a pretty staunch storm, like I mean, obviously tornadoes have higher than 60-mile-an-hour winds, but it's pretty high for normal winds. A windy day here in Texas, you're talking like 20, 30-mile-an-hour gusts, and that's pretty windy. And so 60 is probably upper atmosphere. So friction, again, is only important near the surface. There's nothing to be frictioned against in the upper atmosphere. And it acts to slow the air movement, and it also helps kind of combine with the Coriolis effect. It deflects the air off to the right also. And so they're just kind of illustrating the Earth spinning here. So as the wind comes down, the Earth is spinning this direction because the sun rises in the east and sets in the west. And so the Earth is turning this way. And so instead of just coming straight down, the wind is going to get deflected a little bit. And if I'm going the direction of the wind, it's deflecting to the right. In the southern hemisphere, it would go to the left. And so if that is where the wind is aiming, this is where it's going to end up. And so that's what happens with the Coriolis effect and how everything kind of gets deflected off to the side. So what they're showing you here, how this applies with friction. So here we go. We have low pressure, we have high pressure. So without anything else acting on it, the low pressure and the high pressure, your wind should just be blowing the direction of the red arrow. That's the way it should go. You add in the Coriolis effect, and that's trying to deflect it off to the right. You add in friction, and friction is trying to basically stop it and deflect it off back to the left. You add, just like you will, if you're all taking physics, who's taking physics? Just like you did with vector forces in physics, you add all these vector forces together, and the sum total means that your wind is actually blowing that way for a certain intensity. So there's actually, like, weather, let's be honest, for young people, weather's boring. Weather is one of the most advanced technologically and mathematically intensive things that we're doing today in science. Maybe not like particle physics or anything, but the most advanced computers that you will find in the DFW area are probably working on weather. The weather people have crazy good programs. They do a lot of computation, and all that computation will just get you one weather model. They use multiple weather models over and over and over again to try to build their forecast. In college, one of the biggest computers I ever saw was my oceanography teacher, and he was doing like weather patterns for the ocean and water patterns for the ocean. I didn't even know that Apple made like desktop boxes. And I walked in and he had like 6 of them, like big Apple like PC boxes. Not like, I got a MacBook or I got an iMac or something like that. It was like a big Apple like computing center, and it was crazy. And so when I saw that, I was like, okay, the weather and ocean people are pretty legit. So we got upper air winds and the jet stream. We hear about the jet stream a lot in Texas because it usually affects our weather. Jet stream is basically a river of air flowing through the atmosphere. It's usually high altitude and high velocity, about 120 to 240 kilometers per hour, which is pretty fast. I believe we have like the Gulf Stream, which is a jet stream that kind of comes up through here. I might be wrong about that, but Let's see. Briefly describe the Coriolis effect and how it influences air movement. Basically, as your air moves from high pressure to low pressure, it gets deflected to the right in the northern hemisphere because of the rotation of the Earth. And we can probably stop it there. Yeah, nice. So we got part of the way through chapter 13, and we can probably finish 13 and 14 tomorrow. And then 15 and 16, I believe, are the space chapters. So we should be good to start our signature assignment on Thursday, because today is Tuesday.